Good day, and welcome to Get Your Optimizer to Give Up All Its Secrets. My motivation in putting this session together is to discuss some aspects of the SQL Server Optimizer that I find that many data professionals do not know about. Now, I am a big believer that understanding how something works will help you to use that product better. And this is no exception. We're going to discuss some of the internal mechanisms that happen within the SQL Server Optimizer. My hope is that with the information in this session, that you will be able to write better queries with a better understanding of how those queries get processed inside the SQL Server Optimizer. The PASS organization has many features to offer beyond the PASS Summit. There are SQL Saturdays, which I'm a huge fan of. There are local user groups, virtual user groups, and the new PASS Pro offering. So be sure to check out these many features. Also, your feedback is very important. Please submit feedback for this and all other sessions, and please have them in by the deadline listed on the screen. So here are the things that we're going to be talking about today. First, we're going to set some of the background information that I think are necessary to understand what we're going to be seeing as we dig deeper into the optimizer. Most significantly, to me, we're going to start to look at some of the internal structures that are available within SQL Server, such as query trees, and we'll briefly get into the memo structure. I do feel compelled at this point to issue a word of caution. We're deep into the undocumented space. We're going to be talking about things here that do not have official documentation within SQL Server. What does undocumented mean? It means it could alter from one version to the next. Also, please do not run anything that I'm going to show you today that falls into that undocumented category on a production system. Even be very careful about your test and dev systems. So I do want to point out that this is not intended to be a performance tuning session. We're not going to take a query and try to make it better during this session. However, I do hope that the information that you learn in this session can make you a better performance tuner. And I'm sure it's apparent that we're not going to cover every aspect of the SQL Server Optimizer. There's just way too much to cover in the next 60 minutes. But I do hope that we gain a better understanding of SQL Server internals and that we can figure out ways to write queries better, perhaps from the get-go, or to take existing queries and to make them better. So, as I said, this is only the tip of the iceberg. There are so many things going on inside of the optimizer, and there are actually so many things that we can get the optimizer to spit out to us in terms of information about what's going on that we're just not going to get around to in this session. But I think it's worth it to take the time, if you're interested in this kind of thing, to go further. But I have to warn you, it's a deep rabbit hole. I've been doing this myself for about 5 years, and by no means have I found the bottom of that rabbit hole, and I think there's way more out there that I haven't even considered yet. My name is Brian Hansen. I've been working as an operational and development DBA since 1998. I started with SQL Server 7. That's really where I cut my teeth, although I very quickly inherited a couple of 6.5 instances, and so I gained a rapid appreciation of how much better things got with SQL Server version 7, and it's only gone uphill since then. I work in the nonprofit space in Kansas City, Missouri in the United States, and I am absolutely fascinated with SQL Server internals. The first thing that I want to cover is a couple of background pieces of information that will help us to better understand some of the information that we're going to see coming out of the SQL Server operation. The first of these is the concept of logical processing order. What logical processing order does is to identify the sequence of events that have to happen in order to get the correct results. I want to absolutely emphasize this. Logical processing order is not the same as physical processing order. They are two completely different things. Logical processing order gives us the steps that could be followed and that will guarantee to result in the correct output. Physical processing order is what the optimizer comes up with. It's a better way to find the correct answer. And the job of the optimizer is to do just that. Logical processing order forms the basis for how the query gets initially parsed and input to the optimizer. Now, we're going to be talking about this from the perspective of a select query. Many of the same principles apply to update, delete, insert queries, but we're just simply not going to have time to get into any of those details. We'll cover them just very slightly at the end. One important thing to understand here is that SQL is a declarative language. If you've ever written code in a language like C# or JavaScript or Python, then you know that you outline the step-by-step instructions for something to happen. So for instance, if you were writing, say, something to recover data and basically do the equivalent of query processing in one of these languages, you might have to say, okay, go out to disk and retrieve these records, and then go to, apply this filter to get rid of certain records, and do this, that, and the other thing. You have to outline all of that in a fair bit of detail. But with SQL Server, all you do is you specify what you want. That's the whole point of a SQL query. You're not outlining the details of how that query will be resolved. That's the job of the optimizer. It's going to basically write that program for us. Now, if you're going to write a SQL query, and you sit down at your keyboard, say in front of SQL Server Management Studio, the first thing you're going to type in is the keyword select. Now, if you're like me, a lot of times you don't know exactly where you're going to go from here. That is, which columns that you need. And so I'll put as a temporary placeholder an asterisk, followed by the from clause and where the data comes from. So a table name, for instance. Now, at the time that you typed in the select and you hit the space bar, IntelliSense, whatever IntelliSense program that you're using, isn't going to be able to offer you a whole lot of help at that point. It has no idea what columns are available because you haven't yet specified what table you're pulling from. The point here is that when SQL Server processes the query, it kind of needs to do so in a different order than how you typed the query in the first place. SQL, I think, is intended to be a natural language type of query structure. That is, something like English. And so when you read the query, it kind of has that natural language flow to it. However, the computer needs to process those clauses in a different order, and this is the order in which those clauses get processed. So we start with the from clause, then we get to the on and the join clauses, finally down to where, and you'll notice that it isn't until some point in the processing that we even come to the select clause, which is where our query began. SQL Server has to take apart the query that we type in and rearrange it, in effect. So this here is a kind of an arbitrary query. It really doesn't have a whole lot of meaning. I just wanted to include a number of T-SQL elements in it. Basically, if we take those clauses that we listed out in logical processing order and rearrange them, we get something that might look like this. Now, this doesn't read like a normal query, but this is kind of how the computer has to process it. Now, I want you to think about a couple of things, and we'll just cover the first little bit here. We start by acquiring data from the order header table here. Now, we haven't told the optimizer, we haven't told SQL Server which parts of the data that we want from order header. And so basically, in this logical processing order world, we go out and we retrieve all of the data from order header, every row, every column. Next, we go out and we acquire the data from the order detail table. We haven't yet provided a predicate, a join predicate. So how do we join two tables together without a join predicate? The only way is to do a Cartesian join. So now we've taken two tables and we've done this Cartesian join on them. Every column, every row from table A joined to every row from table B. And we repeat that process with the third table. So even in this very simple three-table scenario, let's say these tables are fairly small, maybe in the 100,000 row range. Doing a three-way Cartesian join on these tables might result in approximately a quadrillion rows or something like that as an intermediate result, before we can even start applying predicates. In other words, it's going to be more than any physical computer today could reasonably handle, either in memory or even spilling to disk. And that's just one of many potential problems that will come up, and it's the job of the optimizer to overcome those problems and to make things better. The second concept that I want to cover has to do with relational operators. Now, I think we're very lucky because many of the principles that come out of a relational database engine such as SQL Server are rooted in a branch of mathematics known as set theory, which has been around since the late 1800s. Now, I'm no mathematician, so what I'm about to say may not be 100% accurate, but I think it's pretty close. The mathematicians who worked on set theory have put together many theorems about set theory that have proven true. Just like we knew from grade school that A plus B is equal to B plus A, for instance, we know that table A, or dataset A joined to dataset B, is the same as dataset B joined to dataset A. They're equivalent. And set theory has worked out many of these theorems that form the basis for a relational database engine. Now, like all mathematics, set theory has its own language and its own notation. Now, there's just a couple of things on this slide that I really want to point out to you that are of significance. You'll notice that many of the operators are very similar to what we work with in SQL Server. Joins help, for instance, come in this inner, outer, and Cartesian format, but we also got the semi-join and the anti-semi-join. Now, these exist within SQL Server, but there's no keywords that correspond to them. I find that many database administrators or data professionals don't understand what a semi-join is. So imagine that we have, for instance, a table of customers and we have a table of orders. And somebody comes to us and says, now, by the way, let's also imagine that in this data set that we have customers who've never placed an order. For instance, perhaps somebody who simply contacted us and made an inquiry of us, we'll add to our system as a customer. Or perhaps we've gone out and acquired lists of people that we find might be interested in our product. And so we have customers who've never placed an order. Now somebody comes to us and says, hey, I want a list of all of our customers who have actually placed an order. Now there's many ways to write a query to resolve that inquiry. We could say, for instance, select customer ID, comma, first name, comma, last name from customer where customer ID in select customer from the order table. We could also write it as an inner join. The important thing here is, first of all, we're only outputting rows from the customer table. And second, we're only looking at the order table to check for existence, to check for some sort of a condition that's related to the relationship between the customer table and the order table. That is a semi-join. An anti-semi-join is kind of the opposite. Somebody comes to us and says, give me a list of all of the customers who have never placed an order with us. Well, we could say something like select customer ID, customer first name, comma last name from customer, where not exists, and then in a subselect we could do select customer ID from order, or select distinct customer ID from order. And that will give us a list of our customers who have not placed an order. That is an anti-semi-join. Again, we're only outputting rows from one of those two tables, customer in this case, based upon the relationship with order table. And in the output, we either output a row from customer or we don't output it. We'll never get duplicate rows from customer. So it's 0 or 1, and that is an anti-semi-join. The second important thing to notice on this slide is that over here on the right-hand side, we have this select operator. Select in relational algebra is the same as what we would call a where clause in SQL Server. That can be confusing because, of course, we have a select in SQL Server, but that does not correspond to a select in relational algebra. Select in relational algebra is a predicate. It's a filter of some sort. Obviously, that can be confusing. But in some of the output that we'll see from internal structures in SQL Server, it will use this notation of select to mean a filter. So what we consider a select in SQL Server, it's called a project in relational algebra. And so we'll see that keyword where we might, in SQL terms, think of a select clause. Now, with that background in mind, I think we're ready to talk about the process of executing a query. Now, we've all done this a number of times. There are some things that happen under the covers that we don't see all of the time. In fact, we very rarely see some of these things. So we have parsing and binding, we have optimization and execution. Now, we can look at this graphically, something like this right here. So here we start off with a query that we're going to pass into SQL Server. It's a bit of text. That text gets parsed, and it gets turned into something known as a query tree. And this here is a kind of a very, very simple generic graphical representation of a query tree. The optimizer will take that query tree and reshape it into different forms. And I know that in this graphic here that they look the same, but you have to imagine that it's doing manipulations on it and we're changing the shape of that query tree. Internally, SQL Server uses a structure known as the memo to consider various alternate forms of the query tree. And we'll very, very briefly look at the memo at the end of this session. Finally, it works out an execution plan, and we should be familiar with that. That execution plan gets executed, and we get results back. Let's look at some of these in a little more detail. The first thing that happens is that the query gets parsed. And that starts with a process known as algebrization. It's also in older versions of SQL Server known as the normalizer. Basically, the purpose of the parsing and the algebrization is to validate that the query is syntactically correct, and to take that structure and to put it into an initial query tree that we sometimes call the parse tree. Now, so for instance, if we pass in a query that looks like this right here, it will pretty quickly fail on us because it doesn't know how to read most of these keywords that we put in here. It has no idea what to do with this query. And so we'll very quickly get a syntax error that comes out of it. So pretty simple. Second, parsing and binding is responsible for taking any views that it might find in the query and expanding them out. So if we give it a query like this, we may initially believe that the from clause is specifying a table. But when SQL Server goes out and looks at the metadata, it may find that it's actually a view. And so it will, in effect, take the text of that view and substitute it into our query. Now this isn't exactly what happens, but for our purposes that's good enough. And so it will insert the text of that view into the query, and then we have something that may represent nothing but base tables, or there may be additional views in there, the evil nested view. And in that case, it will have to repeat this process until we have nothing but base tables being referenced in the query. And then finally, as part of the parsing and binding process, we get to the binding. And this is where we go out and start retrieving some of the more of the metadata and making sure that objects exist and so forth and so on, and making sure that the right permissions exist for the user. And it does a couple of things here that are fairly straightforward, such as data type resolution. So consider this union statement right here. Now, you know that select one is an integer, and select some text is a string. And those two data types are incompatible. So we will get this error message right here pretty much right out of the bat because of that data type resolution that's going on. Also, we do aggregate binding. So if we have this query right here, you may notice pretty quickly that we have customer ID in the query, but that's neither part of an aggregate nor is it part of the group by clause, and that's not allowed. And so we get this error right here. So these kind of things happen right up front during that parsing phase of the query. Now, at the end of parsing, what SQL Server comes up with is a parse tree, or a query tree, sometimes also known as a relational tree. What a query tree is an internal representation of the text of the query. I've got a lot of text up here about what a query tree, some of the properties of a query tree, but I find it perhaps a little more instructive to look at a graphical representation of the query tree. So here we have the same query that I showed you earlier, and something that might be a corresponding query tree. Now, we kind of don't have enough room on this slide, so you have to sort of imagine that this stack of operators over here on the right-hand side is actually up on top here. So we go straight up in a solid stack. So imagine kind of a tall tree there. And the different blocks in here represent logical operators. This is the way that you will see a query tree typically represented in blogs and so forth that address this topic. And this is great and everything, but as I started to study this, I thought to myself, it may make more sense to represent it more like a query plan that we're used to. So imagine that we have this query tree right here, that vertical stack of stuff. So let's take this and let's rotate it 90 degrees counterclockwise, like so. And so now we have this horizontal layout for a query tree. Now, if I pull in a little bit closer, you'll see that up here in the upper right-hand corner, we have the get operator for customer ID. What we really want is the get operator that's down here, which is, I think that's not focusing very well, but that particular operator to appear up here instead. So now imagine that we take this and we flip it and do a mirror image of it, and now this operator appears up here and the customer get operator is down there. So we do that 90 degree counterclockwise spin followed by a mirror flip horizontally. And that's kind of the way that I like to envision these query trees, which means that we end up with something looking kind of like this right here. And now if we take our query over here and we rearrange it using that logical processing order that we discussed and put it into that logical processing order, then we note that the query elements start to line up very nicely with our query tree. So we start with order header here. This is what appears up here in the upper right corner. Order detail comes next. If I can find my, and that comes here. Customer is next. That's here. And then we start to do our different joins. So with our join, and then we have the joins over here, and we have our join predicates. And then everything kind of goes right along the stack here. So we've got our select, which is basically our where clause. We have our group by aggregate. We have our another select, which represents the having clause, because having is nothing but a filter that's applied after the group by is done. Then we have our order by and our top, and these go straight down the sequence that we have in our logical processing order formatted query. So basically, when I said earlier that logical processing order forms the basis for creating the initial query tree, this is exactly what I'm referring to. So this gives us the concept of a logical plan. Now, a logical plan is somewhat similar to a physical plan. That is, it's going to outline the series of operators that get executed in order to come up with the correct answer. But there are no physical properties associated with a logical plan. So we have, for instance, no indexes, no cardinality, we don't even really, at the very beginning, we don't have data types or anything like that associated with the logical plan. Now, the logical plan, basically the initial parse query tree, will get reorganized and reformatted during the optimization process. And so we have multiple logical plans that get generated, and these can be compared. Now, at some point, we can start to substitute physical operations for logical operations, and then do costing on the plan. And of course, a logical plan consists only of logical operators. So for instance, we'll simply say that we need to get some data. We don't care where we get the data from. Does it come from a heap, a clustered index, a non-clustered index? It doesn't matter where the data comes from. We'll say that we're going to do a sort. We don't care if it's a merge sort, a hash sort, or a loop sort. We don't care at this point. We just say it's a sort. So logical operators only. So let's do a demo of how we actually display the query trees. Yes, we can get the query trees out of SQL Server. We normally don't see these, but with the right combination of trace flags, we can. So the first thing that we're going to do is we need to turn on trace flag 3604. And what this trace flag does is to output the results of certain things to the Messages tab. This is a very useful trace flag to turn on for discovering internals, not just what we're going to be looking at today, but well beyond this right here. So 3604 is a relatively well-known, still undocumented trace flag that does just that. So we'll turn that on. I'm also going to set format only on because a couple of these queries would take a very long time to execute, and we don't want to do that. I'm only interested in seeing what comes through the optimization process. So let's start with just a very simple query. This is basically just a select star from customer query. And at the bottom, I'm going to specify option recompile. This will guarantee that this goes through the optimizer. And I'm also going to turn on trace flag 8605 for this query. Trace flag 8605 shows us a particular form of the query tree known as the converted tree. This is not the initial parse tree. We'll come back to that in just a moment. But this is just a particular query tree that's available to us. So when we run this and we look at the Messages tab, we see some extra output here because of these trace flags. And this right here shows us that converted tree. So here's how I read the output. If you look at the indentation levels on each one, each line is going to tell us the particular operation that's being done there, and the lines below it with a greater indentation level are the inputs to that operation. So we have a project operation. The input to that operation is get. So what we're going to do is we're going to get the customer table. You see that it tells us the internal object ID of the table, and that's it. We're going to get the data from that table. Then we're going to come up and we're going to project. Remember, project is basically a select clause in T-SQL. And we're going to output some columns here, so we'll do customer ID, first name, last name, and address and state. So, very simple query tree, hopefully very simple to understand. If we just simply add a where clause into the query, then we can see that here we have a project operation. The input to that is a select operation. Remember, select is a where clause. And the inputs to the select are a get. Again, we're going to get our customer table, get all of the data from that table. And the second input is a comparison operator. This is going to be an equality comparison, and we're going to compare the value of the state column to the constant CA in this case. Then all of that gets input to the select operator, and then out to the project operator where we're going to output our various columns. So again, that corresponds fairly well and fairly straightforward to the query. Now, if you're like me, I prefer to see things visually. So I have here a tool that will allow us to look at these visually. So I'm going to start by doing the exact same things with trace flag 3604. And we'll come down to this query that we just ran with the where clause, and we'll look at the converted tree up here. And so again, this is just the graphical representation of the exact same thing that we saw. We have a project operator. The input to that is select. The select has two inputs. We get the table data, and we have this comparison operator and equality on state equals CA. So simple query tree, and just a nice way, I think, to visualize it. And so we could look at all of these various T-SQL constructs, which is kind of what I've got down here in the demo scripts, to say look at a couple of tables pulled together with a join clause, and we can see now that we have a join operator in here. And the join operator gets three inputs. First input is the first table, second input is the second table, and the third input is the predicate. So we get from order header, we're going to join to customer, and our predicate is the equality of one table's customer ID to the other table's customer ID value. And then that gets projected out into our various columns. So pretty simple queries and very straightforward stuff. Now, as we come down here, we'll start to see trace flag 8606. Now, what 8606 will do is to give us some additional query trees in the output, including the input query tree. So here we have a query that's going to take two tables, join them together, and do a group by. And it's going to output the input tree, the simplified tree, the join collapse tree, and a couple of other trees here. Now, I'll just run that real quick, and we won't really look at them in great detail, but these are the various trees. The other thing that we can do is to combine those two trace flags, 8605 and 8602 together into one query here, and we'll get all of the query trees that we've seen so far. So I'll run that. So we have the converted tree that we've already seen, but let's look at the input tree first. Actually, let's look at a couple of elements of this particular one that we haven't talked about before, and that's the group by aggregate parse in here. So in this particular case, if we look back at our script, we are grouping on account of order ID grouped by customer ID. So looking back here, we can see that we're going to take our order ID, that's our grouping element, and we'll pass it into this aggregate function logical operation here, or scalar operation. And we're going to, out of this, project an expression, and that expression is the count. One thing about these query trees is that you don't see every single detail that is sometimes useful to understand what's going on in the query. It kind of leaves some things out, which is, I find, very annoying, but that's the way it is. And then up here we're going to just simply do that group by aggregation there, and output that to the projection. So it's kind of this taking all of this stuff and combining it together. But let's back off here and let's look at the input tree. And there's one thing in particular on the input tree that I want to look at. So with this particular query, we're taking table order header, and we're joining it over to customer table. And here's our predicate, customer ID equals customer ID. And so if we come over here and look at the input tree, we get just that. We have our join operator, we have order header table, and customer table, but they come together, and the third element in this, the third parameter, if you will, to the join operation is this thing right here, which is a constant. And that constant has a value of 1. Well, what does a constant value of 1 mean in terms of the join condition? Well, 1 in many computer operations means true. And so what we're doing here is that we're always, in other words, for every row in the order header table and for every row in the customer table, we're going to join each row to each row. This is a Cartesian join, a cross join. And so like I said before, this is kind of how this is the logical processing order at work here. These tables are being joined in a Cartesian fashion, and then the next thing that happens is that we have this select operator here, which is taking the customer ID and the customer ID from each table and basically applying this as a filter after the fact. And if you're familiar with old style SQL syntax, before there was an on clause, this is how you would write queries. And so we see that in the query tree. Now, we've already briefly looked at the converted tree. We can see how the shape changes. We come into the simplified tree, and the shape changes again. This is definitely, the simplified tree is going to leave a few things out of it, but kind of maybe less importance. And then it's not uncommon to see some of the later tabs be identical. I have yet to see anything where the tree before project normalization and the tree after project normalization are different, although I'm sure that it happened. This script is available to you, and you can look at the various different T-SQL query elements in here and look at the output query trees for them and for yourself, and kind of see what happens during different as you apply different T-SQL elements. I do want to point out one last query here, and this is just select star from sysObjects. And so if I execute this query and look at the converted tree, just the converted tree, you can see that we get something that is a little complicated. It's more than just a simple, when we looked at select star from customer before, we had something that was really simple. Here it's not. The thing to understand here is that sysObjects is really a view under the scenes, and we can see that there's a lot of stuff going on here. There's a lot of complicated stuff going on under the scenes, and with views that can happen very quickly. So let's go back to the slides. Next, let's talk a little bit about the optimization process. So there are several steps in optimization that happen here. First we're going to talk about is simplification. Now, For SQL Server, it's kind of important to put queries into standardized formats. That is, you can write a query in many different ways, but it prefers to do some internal rewrites of that query. And I say that as though it's actually manipulating text. It's not. It's really manipulating those query trees. But it does these internal rewrites of the query into more standardized formats. Simplification is one of those steps that will help to accomplish that. And we'll actually go through this in a lot more detail here in a demo in just a moment. But we first have this simplification step. Next, SQL Server will go out, or I should say the optimizer will go out and retrieve some of the statistics and some of the other metadata about the objects that are being referenced in the query. It will do cardinality estimation, which is a complicated topic in and of itself. Cardinality estimation, though, is one of the things that's important to understand about that is that it changed significantly starting with SQL Server 2014. Now, by this point, 2014 may be old enough that we're hopefully not dealing a whole lot more with those older versions, but they are still around, and we do need to be aware of it. Also, we have databases that came from those older versions that have been put onto an updated version of SQL Server, and it can still impact those databases until we take certain steps, such as upgrading the compatibility level of the database. So we do need to be aware that there are a couple of versions of the cardinality estimator out there, and realistically, every version since 2014 has made upgrades and improvements to the cardinality estimator. So it's almost like we have a cardinality estimator for 2014, 2016, 2017, 2019. They've each got their own version of it. Like I said, it will also go out and retrieve other metadata. We've got examples of this are, is the data in a heap? Is it in a clustered index? Is it in, what are the sort orders of these indexes? What are the data types? What constraints exist? What keys exist? What nullability constraints exist? All things like that, and much more that get pulled that affect optimization and that SQL Server needs to know about. SQL Server also looks for what's known as a trivial plan. Now, a trivial plan is one which I say on here that it can only be executed one way. That's not 100% true, but there's only one reasonable way to execute the query. So for instance, if I say select some columns from customer, really the only way to resolve that query is to read through the entire customer table and return every row and every column. If I say select from customer where last name equals Hansen, and there's not an index on Hansen, it still has to read through the entire table and then apply a filter to come up with the results. Now, as an example of a case where there's multiple ways to execute a query, but it still comes up with one as trivial, if I say select from customer ID where customer ID equals 17, and customer ID is the primary key in the clustering key on that table, then it really makes sense just to do a clustered index seek straight to that ID and return that row rather than scanning the whole table. There are two ways you could execute it, but one of them doesn't make any sense at all. Next, the optimizer goes through what are known as search phases 0 through 2. We're not going to go into tremendous detail on these. They're fairly complicated, but we'll just do this much. Search phase 0 is called transaction processing, and it basically just does some very simple, looks for some very simple query shapes, very simple, very common query patterns, and sees if it can just come up with something super quick as an execution plan. It will cost out that plan, and as so long as the cost is below some internal threshold, that threshold is not documented and I think probably changes from version to version, but as long as it's below some magic threshold, it will just immediately come back and say, this is the plan we're going to use. If not, however, it'll go into search phase 1. Again, this is looking at some additional common query shapes. It's not doing a whole lot of complicated work. It again has that that internal threshold that it's looking to meet, at which point it will, if it's below that threshold, it will exit out and give us a plan. Notice that this is the first time that we start to explore parallel plans. And then finally, it will go into search phase 2, full optimization. And full optimization has at its disposal all of the rules, the transformation rules that are available within SQL Server. The transformation rules change the query tree from one shape to another, equivalent. And it can operate not only on the entire query tree, but on subsections of the query tree. And so as it comes up with these alternative equal plans and does physical costing, it will eventually come up with these different plans that have different costs. And it will either, first of all, exhaust every possible plan, that's kind of rare, or it will hit some sort of a timeout. I say sort of a timeout because that's not the full picture, but for all intents and purposes, we'll say it timed out. And at that point, it will output the best plan that it's found so far. Now, the number of possible plans on once you get beyond the most trivial of queries, the number of possible plans becomes astronomical very quickly. So it can't possibly search them all, and because it can't search them all and it's going to try to find the best one, it needs to apply some rules to figure out what's the best way to search rather than just starting from A and going to B. It needs to kind of jump around and figure out the best way to do it. And so these are the heuristics that I refer to here, things that it can do so that it doesn't have to look at every single possible query, and that it can look at them in a smart order. These aren't always 100% perfect, but they generally work pretty good. Of course, at this point, SQL Server will construct the execution plan, and it will stick that plan in a cache so that the next time the same query is executed, or at least a very similar query is executed, you can go out to the plan cache, find it, and not have to go through that optimization process again. That query plan is stored in the cache based upon a hash value on the query text. It's also important to note that the so-called set options, so set ANSI nulls on or off or things like that, will impact the optimization process. Therefore, those become an important attribute that gets stored in the plan cache, and if those attributes change, then it needs to go through the optimization process again to make sure that it's finding the best query and the most correct query for that particular set of situations. So I promised a moment ago that we would look more at simplification, and let's do that right now in the form of some demos. Here we have some queries that will hopefully help us to understand the simplification process a little bit better. The first thing that I'm going to do is to turn on estimated execution plan by hitting Control L with this section highlighted. And we look at the results of these two queries, and we can see pretty quickly that they're identical. Let's look at the queries themselves. So in the first one, we're using a subquery, an in clause, to find all of our customers that are in California, and then we're looking up their related orders. In the second one, we're doing the same thing with an inner join. These two queries are logically equivalent, and we can see in the execution plans that SQL Server has recognized that they're equivalent, and it's done some rewrites and converted that in clause into an inner join. Next, let's look at foreign key table removal. So in this particular statement, we have two tables that are being joined together. However, notice that we don't actually output anything from the customer table, and we're not using anything from the customer table in any way, shape, or form in this query other than in our join statement. There's no where clause that references it or anything like that. If we look at the execution plan here, we can see that it has removed the customer table from the query. Now, it can do that because we have a foreign key between our order header table and customer. So it knows that the customer record must exist. If it didn't exist, then it would have to include the customer table just to validate that that existence is there. And that would be the only reason to write a query like that in the first place. So let's turn that foreign key off. Let's try the same query again. Look at the execution plan, and now you can see that it does have to go out and pull data from the customer table. Next, let's look at contradiction detection. So if we look at this query here, we don't need to know anything about the underlying data to know one thing. We're not going to get any results back because we're telling it to give us only the data where the price is greater than $50 but simultaneously less than 25, and that can't happen. So we know that when we run this, we get nothing back. If we look at the query plan, though, we notice something interesting. SQL Server recognizes that it doesn't even need to access the table. Not at all. There's no data access whatsoever here. Just this constant scan, which is basically just returning the metadata. So that you remember when we ran it, we actually had the columns come out here. So that's basically what exists in that constant scan. Like I say, this is just a poorly written query. But let's come up with a couple of cases where maybe it's not so obvious. In this case, I'm going to create a view called Important Customers. And in my Important Customers table, I'm only going to put California residents. And then I want to select from my Important Customers table where their state is Missouri. Now, we know that this is a contradiction. Somebody can't have a state attribute that's both California and Missouri at the same time, and so we're going to get no results back. The question is, will SQL Server recognize this as a contradiction? Will it just do that constant scan? And interestingly, it does. It recognizes that that's the case. And this makes sense because you remember I said before that when it sees a view in the query, it's basically going to expand that view out and put the text of the query in there. And so the query tree itself has the contradiction. In the query tree itself, it's going to say that the state is California and the state is Missouri. And so it will detect that contradiction. Let's go a step further. Let's create a products table that only contains products that are under $1. I'm going to call that cheap products. So only products that are under $1. I'm also going to put a constraint on the table so that the price can only be between $0 and $1. And that works. So now, if I run this query right here and say, give me all the products that are greater than $50, we know that there can't be anything in that table. We haven't put anything in the table that's more than $50. And further, we've put that check constraint on there to prevent it from being greater than $50. So no results will come out. And again, if we look at the query plan, we can see that it detected that contradiction by reading the constraint information, and it knew that there could not possibly be any results from this query. So one of the very important things that comes out of these simplification demos, I think, is the understanding that constraints matter. In this particular case, a check constraint affects the optimization. In the previous demo where we did foreign key table removal, we could see that the foreign key affected optimization, where it could entirely drop a table out of the query plan because of that foreign key's existence. Constraints matter. And I know that there's a lot of push, especially among some developers that I've worked with, and I'm not saying anything bad about developers here, but some people that I've worked with who think that constraints are unimportant. We'll do everything in the application. We'll check all of these things in the application. But as we've demonstrated here, those constraints do affect optimization. They do affect them for the better if they are in place properly. And so it's always best to have them there. There are a couple of DMVs that are kind of interesting to look at here. The first of these is called exec query optimizer info. There's 3 columns that are of particular interest to us. The way that this DMV works, the way that it outputs information, is that you have basically these 3 really important relevant columns. So the first column is the name of an observation. An observation might be number of tables used in the query, the number of times that an optimization went into search phase 2 or something like that. Then we'll have a counter that tells us how many times did this particular observation happen. That's the occurrence column. And then finally the average, the number of times that it was used. Now, this particular DMV is aggregated, and it goes back to the time that the system restarted. So you just get a whole bunch of numbers in there that by themselves are relatively meaningless. Where it becomes meaningful, though, is that if you can capture just one optimization happening, you can see some of the details of what happened in that particular optimization. The way to do this is to, basically you need to be on a very quiet system. It's going to probably be a dev system, preferably that nobody else is using at the time, and that you go in there, you capture this DMV, capture the contents of it before you run the query, then you run the query, and you capture the contents of the DMV afterward, and then do a difference between the two. And if you do that, you can see what happened just during that single optimization. So that's some interesting and useful information. The second DMV to look at here is called exec query transformation stats. And this is going to give us 1 row per transformation rule. So it has all of the transformation rules listed out, 1 per column, 1 per row. Now the transformation rule names are a little bit coded. They're kind of these short abbreviations that sometimes you have to really work to make sense of. Basically, though, this rule is going to tell us how many times, or this DMV is going to tell us how many times was that particular rule attempted to be incorporated into a query, and give us some information about that. So again, some very interesting information. I promised you a couple of times that we would take a look at the memo structure very briefly at the end of this presentation. As SQL Server goes through and does different substitutions into the query tree, different explorations, different implementations, and it comes up with various query trees, some of which may be logical and some of which may be physical, and there may be a hybrid of the two, then it needs a way to start comparing those queries against each other. And so as it comes up with those physical alternatives, it starts to stick them into this memo structure. I personally have found the memo to not be that terribly useful of a structure to understand and to really get into the details of in terms of making your queries better. It really, I haven't found it that helpful. Maybe it is, maybe there's something there, but that's not been my experience. So let's wrap things up. I just want to end by saying, oh my gosh, the optimizer is super complex. We've been dealing here strictly with select queries. There are, however, so many more things that the optimizer has to be aware of and to know about and to deal with. There are all kinds of constructs within SQL Server that go well beyond the traditional row store. And what I've got on these last 2 screens here is really just the tip of the iceberg. There are so many things that the optimizer has to take care of. It is truly an incredibly complex piece of code. I mentioned before, SQL is a declarative language. You're giving SQL Server a specification of what you want, the results that you need to get out of the database in order to do whatever you're going to do. That specification is taken by the optimizer, which in turn writes a program for us, and that program is then executed. That being said, in practice, no piece of software is perfect, and the execution plan that we may get out of a query may be suboptimal. And it may be suboptimal in very noticeable ways. And when that happens, we kind of sometimes have to outsmart the optimizer by rewriting the query in a way that it will work better and will work more efficiently. So I want to thank you for attending this session today. I'm TF3604 on Twitter. My email is on the screen as well, and my website is tf3604.com. With that, let's go into the Q&A portion of this session.